And we can move toward the third presentation. The third presentation is about a stability analysis of explicit material point method, and the work is authored by Songbei and Craig Schroeder, and Craig is actually going obviously to do the presentation, right? And they are both working at the University of California, Riverside.
I can't also make this share.
It's good. It's good. We can see it in my line. Perfect.
All right, thank you, everybody. Thanks for attending my talk. This is some work I did at UCR with my graduate student Songbei. We're analyzing the stability of explicit material point method. So you've already seen it a little bit yesterday. Material point method is a simulation technique usually used for complex materials, foams, gels, in this case, sand. We're going to attack this in two pieces. The first piece is we're going to be looking at the interior of the material, which we can do with von Neumann analysis. And then we'll be looking at the boundaries of the material, which we'll do by analyzing single particles. So to begin with, we take a look at this CFL condition, classical CFL condition. What is this? It says that the numerical information speed in a simulation needs to be at least as large as the physical speed. Why is that? Because if the information that I need to get the correct answer someplace in my material hasn't reached me yet in my simulation code, then I cannot possibly be getting the right answer. For example, if somebody is throwing me a ball and the ball is traveling faster than it can propagate through my mesh, then I have no chance of getting anything right. And the way that that manifests in code is it explodes. Yeah, that's instability. Typically with a mesh, you calculate it as saying that I transfer one grid cell per time step. Okay, physically, the information speed is usually the sound speed. We can solve this for time. Typically, we'll throw in a little fudge factor. Here it's new. That's their CFL number. Conventional wisdom says that this is going to be 1. For many finite difference schemes, you can calculate it out and find out that it is in fact 1. But for the material point method, it doesn't necessarily have to be, because we are looking more than one cell. We have these transfers. So it could possibly be something higher. It could possibly be something lower. In practice, everybody assumes it's 1. And usually you'll see people running with the CFL number like 1, 0.95, 0.9. I've seen them as low as 0.5. And this talk may actually give some ideas as to why that might have been. All right, von Neumann analysis. What is this? It's the gold standard for analyzing stability in linear finite difference methods for linear partial differential equations. Big mouthful. But the idea is it's necessary and sufficient. And it's basically just taking the Fourier transform of the PDE and of the method for solving it. All right, first problem is MPM is none of these. It's not periodic, it's not linear, and it's not a finite difference scheme. Interesting choice. It would seem like a really bad choice, but believe it or not, we're not the first people to do this. We're not even the second. And in fact, people have done this in one dimension before. I don't know that one-dimensional MPM has a lot of uses, but it's been done before. All right, first let's take a look at it on an actual simple canonical problem. This is the one-way advection equation. Discretize it. This is forward space, forward time. By the way, not a good scheme. We're essentially going to be looking for solutions of this little form here. So we have a red piece, which is, sorry, we have a green piece first, which is basically waves. It's periodic, it's oscillating in space. And in time, it is growing or decaying. There can also be some oscillation parts. If it is complex, that's fine. How do we get to this? It's basically just obtained from the Fourier transform. It's really just a Fourier transform in disguise. Right, and it's this red part that's going to tell us if we're stable or not. Okay, it's the growth factor. If we look at the two little examples below, we have this little sine wave, and it's basically translating to this right. In the blue case, it's translating and decaying ever so slightly. And in the red case, it's translating, but it's exploding. Okay? Which means if we simulate this for a little bit of time, it's just going to blow up. All right, so the red one is unstable, the blue one is stable. So all we have to do is plug in something that looks sort of like the solution above and calculate the G's. All right, what does this look like for MPM? For MPM, we're going to assume that we have a nice periodic arrangement, same distribution of particles in every single cell. It can be more than one particle per cell, which you see here, that's fine. We have a velocity for every particle, that's fine. It'll just be some perturbation. Same for perturbation of C, which is the velocity derivatives. And then F, as we see before, is a perturbation off of the rest configuration. Okay. The blue part is epsilon. We're just doing a slight perturbation, so it's a tiny number. The reason for putting in there is during the analysis, when you get epsilon squareds and things like that, you can throw them away. The red part's the growth factor. It's exactly the same thing as our advection canonical little thing. Wave solution looks the same. The Z here is our wave numbers. And then finally, the purple part is because we want to be able to have more than one particle in a cell. And the different particles in the cell may have different solutions. All right, I'll bore you a lot of algebra. I'll show you what the conclusion was. The conclusion is the CFL number doesn't actually have to be 1. In a couple of cases it is. So quadratic splines, APIC and CPIC, 1 is in fact, turns out to be the right number. Very interesting surprise, at least for me and probably a lot of other people, is PIC is usually known for being so dissipative that nobody can use it. I've never seen an MPM paper ever use PIC. If anything else, they'll do like a blend with flip or something, or they'll do APIC. They never use PIC because it's so dissipative. It is, in fact, less stable by a factor of about 70%. And then, of course, cubic splines, it blends things out over a little bit wider area. And so maybe it's not so surprising to see that you can run a little bit faster on it. OK, that's interior. Let's switch to exterior here. This is a rotating circle. It's obeying its CFL condition. We're not violating anything particularly bad, but the boundaries don't look good. We're flickering at the boundary. We're not stable there. All right. Why are we stable? We're taking too large of a time step. Okay. It's not obvious why, but we are apparently taking too big of a time step. Lower it down a little bit, and now it's stable. Great. We found a time step size that makes the simulation stable. Except we haven't. If I throw out some particles from the simulation, I leave everything else the same, the particle distribution is the same, stiffnesses are the same, time step sizes are the same, we're not stable anymore. Okay? So this fact that we were stable is kind of an illusion. If the shape of this thing had changed a little bit for some reason, we could just explode. Because we're not really stable, we're getting lucky. All right, stabilize it, make the time step size smaller, great. Nope, still not stable. Send out some more particles, especially when you start getting particles that are isolated. This is looping fast because it's exploded and it sim stopped. But when you start getting isolated particles, it still explodes. Okay? It turns out that having neighboring particles makes MPM more stable because of the averaging back and forth. Once particles become isolated, we have essentially our worst possible case, which leads to, oh yeah, and if we use the time step size, I'll show you later, it stabilizes it for good. Okay, all of this suggests that if we want to understand the worst way in which boundaries can behave with MPM, we need to look at the behavior with single particles. All right, assumptions, stationarity, particles not moving, but it can be anywhere within a cell. Next thing, we're going to be perturbative again, fine. So we're looking around the rest configuration. We're just looking at tiny perturbations around it. That linearizes it. Why is that good? Because it means that the transition from frame to frame is now just a little matrix. It's denoted N here. A little bit of context. M is encoding the forces. It encodes the dt. So this N is a function of dt. It also includes a little bit of information about the spline. It's fine. R encodes the scheme that we're using and also some spline order stuff. All right, and what do we need to do? We need to find a time step size such that the spectral radius of this matrix is less than or equal to 1. What is the spectral radius of a matrix? It is the maximum absolute value of any eigenvalue of a matrix. All right. Who wants to do eigenvalues of an 18 by 18 matrix? Analytically, symbolically, by the way, not numerically, it has to be symbolic. And then we have to find a bound so that dt keeps the spectral radius less than 1. Good luck with that. We did it. It worked. You can actually do it. It wasn't easy, but we did it. Here's the conclusion. Well, it's kind of nasty. If you're familiar with CFL restrictions from fluids, this actually might look relatively familiar. The little green part is mass over volume, that's density. The blue part is the scalar multiple of the bulk modulus. What is the bulk modulus? It's basically a measure of resistance to volume change, okay? In particular, if you're used to fluids, this would be a P wave speed, okay? Or just solid in general, this would probably be a P wave speed for CFL, which is the speed at which sound propagates through the material. So here we're looking at compression, not waves traveling. So it's a little bit different. And then, of course, the purplish stuff is the part that depends on the steam and the spline orders and things like that, the very specifics of the actual underlying integration scheme. All right. That leads us to time step sizes. All right. Normally with simulation, you assume that there is a stable time step size and that you are free to take any size, any time step size as that or anything less than it, okay? This is the kind of the underlying pinnings of variable time step sizes. Every time step you do some calculations and you figure out, okay, what is stable to do this time step? Let me take that size or 0.9 times it or something like that, and it's fine. That's important because different portions of the material may have different stability requirements. For example, some parts are stiffer, some parts are not. What we found through very painful trial and error and debugging is that if you cycle different time step sizes, the stability properties can be radically different. Okay? In these little plots here, white is stable, black is unstable. The diagonal dotted line in purple is when the two time step sizes are equal, so this is constant time stepping. That was basically where the analysis occurred along the purple line. The red dotted box is the time step restriction that we just showed a little bit earlier. And you can see that in some of these cases, hopefully you know the people on that city, we go a little bit inside of our box. Okay. So there are time step combinations that are unstable that we predicted would have been stable. Okay. When we do a little bit longer cycle, so time step followed by 2 of another one, the region gets more complicated and we get more little spots inside of our safe box, so to speak, and also smaller time step sizes that fail. Longer cycle, we can see that we're failing at much, much smaller time step sizes. And then the really depressing picture. We have really, really small time step sizes that fail. And in fact, there doesn't appear to be a lower bound. What does that mean? It means that I am pretty sure nobody will ever publish a guaranteed stable time step size for explicit MPM with APIC or CPIC. I'm pretty sure one doesn't exist because this sort of procedure basically generates a counterexample. Yeah. A little bit depressing, but I'm just the messenger. Don't come after me. I'm the bearer of bad news. And the paper still got in. All right, this is an example. It's a very simple simulation. It obeys its time step restriction. It obeys all the usual, do good things, choosing time step requirements. And it's not really stable. Where do we see the instabilities? Look here, and there's also a little red particle that gets emitted from the mattress, from the blue thing, and it's flying around in the scene. You'll see it in red if you look very carefully. Okay, this is not stable. Solids should not randomly emit particles. That's not desirable. If we obey our time step restriction, all that goes away and everything's fine. Here's another fun one. Surely this would be easy. There's the particle emission. And by the way, the coloring on the sphere is velocity and magnitude. So blue is basically really small. And all these other colors you see on the side where it's flickering through the rainbow, that means that the velocities are getting bigger. Well, why are the velocities getting bigger? There's nothing happening there. I mean, literally the thing is uniformly translating and we have instability showing up. If we do the time step restriction that we suggested, then problems kind of go away. We're okay here. All right, here's another one. Okay, so some interesting things are happening in here. Yes, we have more dynamics, great. We have things shattering into lots of little pieces. You can see some individual particles being pushed off. That's all fine. But it's stable. Okay, it's not exploding. Everything's fine. We're handling single particles okay. In practice, things are pretty good. If we don't obey the single particle stability requirement, shortly after the collision happens, the simulation just stops. It just explodes and it fails. If we satisfy the extra stability requirement, then these simulations can actually keep going and they work okay. And then let's do one more. These are some billiard balls. It's very stiff. Stiffness isn't a problem. It doesn't really matter. Even this simulation is not actually stable if we don't follow this time step restriction. So quick little overviews. CFL stabilizes the interior. Single particle instability stabilizes the boundary. See the paper for details. See the technical document. Sorry, see the paper for bounds. The technical document for details with lots of details. And with that, I'll open for questions. Thank you.
Thanks a lot. And I think we can all thank you also for the very useful theoretical analysis that you've done, and which is of course probably that will be very useful for the community. So we have questions.
Thanks, it looks very interesting, surprising work. I have to forgive my ignorance here, but in the MPM literature, they often talk about cell crossing stability.
Yes.
Is that part of what you've done here? Is that?
No, that's, as far as I understand, that's because the engineering community doesn't understand that you should use linear basis functions for interpolation. If you use quadratic splines or cubic splines, all of that kind of goes away. Yeah.
Other questions? Like, do you think in the future somehow this can open the way where we need to adapt the time scale or even sometimes the scheme or the integration scheme based on the local geometry?
I don't really see that so much. I can see something where you would say, okay, I have particles that are starting to become isolated now. I need to be a little bit more careful about my thing, or like, oh, my energy is starting to increase, you know, maybe it'll take time. I mean, this, to some extent, these things I think have actually been explored a little bit before. That's not particularly unreasonable to do. I had a paper a couple of years ago where it's explicit, so you can actually, at the end of the time step, say, okay, what would have been a good time step to have actually taken, and then just shrink the time step down and be done with it. And it actually, that sort of thing works okay too. So there are some games you can play, but at the end of the day, you kind of need to just understand what time step sizes you can take and efficient ways that you can calculate them.
All right. If there is no other questions in the audience, I think we can thank you again.
Yep.